You've designed a beautiful ROS2 system. In the lab, it works perfectly. But take your robot 20 meters out into the field, and the motor control locks up. The motion gets jerky, and the system freezes. On a wireless network, random packet loss, usually between 3 and 5%, forces the middleware to struggle with its own communication rules. We are going to fix this by writing a custom quality of service, or QoS profile. By adjusting a few parameters, you eliminate that physical jitter, prevent out-of-memory crashes, and guarantee your nodes talk. Software designed in a vacuum fails in the dirt. Tuning your QoS is how we force our code to respect the harsh realities of physics and networking. Let's look at how it works. Most robots have two very different types of data. You have one-off configuration messages that must arrive perfectly, and then you have high-frequency data streams, like an IMU or a motor command running at 50 Hz. By default, ROS2 treats everything as a critical message, using a reliable delivery policy. If the network drops a packet, the middleware will relentlessly try sending it until the subscriber confirms it arrived. For a motor command, a dropped packet triggers a retry loop. Arriving 50 milliseconds late, it's obsolete, pushing subsequent packets out of alignment and causing stuttering. Switching to a best effort policy fixes this. Dropped packets are forgotten, perfectly preserving the 20 millisecond schedule. Here is how you apply that to your code. In your ROS2 node, import the reliability policy module. Then, inside your QoS profile definition, set the reliability parameter to reliabilitypolicy.bestEffort. In real-time robotics, dropping an outdated command is safer than stalling the entire control loop to wait for a retry. Now that we've stopped the retries, we have another issue to resolve. Unpredictable network lag can still occasionally deliver a delayed, useless message, even when you're on a best effort policy. To prevent the robot from acting on old information, we need to enforce a strict real-time window using a finite deadline. A 50 Hz control loop means we expect a new command every 20 milliseconds. Importing the duration module and setting a deadline of 20 million nanoseconds ensures the middleware silently rejects any message older than that exact window. Strict timing prevents jitter, but total network disconnections introduce a different failure mode, memory exhaustion. If a subscriber node drops offline, ROS2's default history settings leave memory buffers unbounded. The publisher will quietly hoard thousands of outgoing messages in the background until your onboard computer completely exhausts its RAM. You protect your hardware by explicitly capping this buffer. Always set the depth parameter to a low number, usually just 1 for a sensor stream, so you only ever keep the absolute latest reading in memory. Defining explicit boundaries for your timing and your memory turns a fragile script into a resilient, hardware-aware control system. There is one major pitfall when tuning these settings. The most common error developers make is modifying the subscriber's parameters while forgetting to update the publisher. This violates ROS2's strict internal law, the QoS matching rule. If your publisher and subscriber policies are incompatible, the system will not warn you. It won't throw a loud error in the console. The two nodes will simply ignore each other in total silence. To diagnose a silent connection, start in the terminal. Run ROS2 topic list-t to display all active topics on your network. Once you find your topic name, inspect its exact policies by running ROS2 topic info, followed by the topic name and the -- for verbose flag. Look closely at the publisher and subscription counts in the resulting output. If you know your node is running, but you see a subscription count of 0, you have found the definitive signature of a QoS mismatch. Take the policies reported in the terminal and cross-reference them line by line against your Python script to ensure total alignment. A robotic network is only as strong as the mutual agreement between its nodes. Verifying these connections in the terminal is just as critical as writing the code itself. Once your policies match and your code is deployed, the physical results speak for themselves. The robot navigates continuously with zero mechanical hesitation. This performance across a degraded Wi-Fi connection happens because we prioritized new data over perfect data and stabilized the onboard memory. This table summarizes our rules. Use a best effort policy, a depth of 1, and a finite deadline for fast motor and sensor streams. Keep the reliable policy for critical configuration data and pair it with transient local durability so late subscribers never miss it. These parameters create a system that withstands the packet loss and latency of a real-world environment. With the nodes communicating predictably, the next step is defining what they say to each other. Join me in the next video to build custom ROS2 message types.